As was said, my name's Lindsey Kuper, and I'm a research scientist in the Programming Systems Lab at Intel Labs. And this talk is about the work that my colleagues and I have been doing on finding and exploiting parallelism in a productivity language for scientific computing. So to motivate the talk, I'm going to start by explaining what I mean by a productivity language for scientific computing and why we care about this problem. And then I'll show you what we've done. And I'm happy to take questions during the talk, but it shouldn't be a long talk, so there will also be time for question afterwards. So imagine you're a scientist or an engineer working on some numerical application. And this might, in fact, actually describe some of you, so it won't be very hard for you to imagine. So you might be working on any number of things. You could be designing a bridge, decrypting a message, picking a stock portfolio, processing an audio signal, training a car to drive itself, and so on. And the mathematical tools that you use for these kinds of applications might include things like differential equations, Fourier analysis, trigonometry, linear algebra, matrix computations, and so on. And you're an expert in those things. And they are what you want to be thinking about when you write your code. But chances are that you are not an expert on things like how to manage memory in a programming language, or how to schedule parallel tasks across compute resources. So when you're writing code, you want a programming model that frees you from having to think about that stuff. So in other words, you want what I'll call a productivity language, a language that enables you to get stuff done at a level of abstraction that matches your domain expertise. So typically you would use a language like MATLAB, Python, R, or Julia. And these languages give you a high-level programming model, so you don't have to think about stuff like memory management or thread scheduling. And they typically come with an extensive set of libraries for doing the kinds of things that you would want to do, like matrix multiplication or FFTs. But if you have a working prototype in one of these languages, there's a dilemma that arises when you want to scale up your code to run on a larger input size or for more iterations or at a finer granularity. And the productivity language that you're using turns out to be too slow. So now what do you do? Well, the usual approach is that you have to port the code from the productivity language to what I'll call an efficiency language, like C or C++. Or more likely, you have to enlist the help of someone to do that for you. In fact, maybe some of you have been the grad student who was brought on to do this for some project at some point. And this takes considerable time and effort, right? Doing it right requires expertise in the efficiency language, as well as expertise in high-performance computing tools like MPI, maybe. And you end up with code that is, in fact, faster and more efficient than the original, but it's also more brittle, it's harder to experiment with, and it's harder to maintain. So you're also likely to introduce bugs at this stage, so that's no good. So rather than asking someone to become a human compiler, it would be great if we could just avoid writing code in the efficiency language altogether and instead use the productivity language at every stage of development, from experimentation and prototyping all the way to running at full scale on high-performance hardware. But how do we actually do that? Well, a lot of people want this. So our lab's attempt to address this problem is a system called Prospect for high-performance scientific computing with a productivity language. And at a high level, the idea is to identify implicit parallel patterns in source code, like map, reduce, array comprehension, and stencil. Stencil is kind of the odd one out. I'll talk more about that later. And these are things that, for the most part, already appear in user programs, especially if the programmer is writing code using high-level array operations, which are common in scientific computing anyway. And then we can compile those to explicit parallel for loops. And importantly, we can do some aggressive optimizations along the way so that we can avoid the runtime overhead of things like array bounds checks and intermediate array allocations. And we've implemented all this as a library on top of the Julia programming language. So Prospect is implemented as a package for Julia called parallelaccelerator.jl. And I'm very excited to note that our team just released our first version of Parallel Accelerator as an open source project last week. It's up on GitHub, and you can go try it out. So the key part of the interface is a macro called ACC. This is the syntax for macros in Julia with the @ sign. And that's short for accelerate. So the way it works is you import our package, and then you can annotate functions in your code with ACC. And doing this lets you designate the parts of your Julia program that you want to compile to optimized native code. And under the hood, this Parallel Accelerator package is a Julia to C++ compiler. that is itself written in Julia. Thank you. So it compiles your code to C++, and then it hands it off to an external C++ compiler. At the moment, it's either GCC or ICC, which will then compile a native library. And then finally, on the Julia side, we generate a function that calls into that native library and calls to your ACC annotated function get replaced with calls to that native code. So I'm going to talk a little bit more about Julia and about the architecture of the compiler. But before I do, my colleagues insisted that I put some actual performance results early in the talk. So here they are. And I'll show more performance results later, but this is a preview. So here's how we do on the Blackscholes option pricing benchmark. So this is a computation involving several arrays of 100 million elements each. And from left to right, we're looking at 5 systems here. So first there's MATLAB in both multi-threaded and single-threaded versions. And then Julia. This is just running single-threaded because Julia doesn't support multi-threading yet, although it's coming soon. And then our system, Prospect, in both multi-threaded and single-threaded versions. And this is on a 20-core machine. So what I think is interesting to point out here is that we outperform MATLAB and plain Julia even when we're only running on 1 core. And the reason for that is that even before adding parallelism, we really get rid of a lot of runtime overhead from things like array bounds checking and allocation of intermediate arrays. But then we add parallelism and we do even better. As I said, all this is on a 20-core machine, and I'll show a demo later on a rather less beefy machine, so you can see what that's like. And I'll show you what the code looks like too. Back to Julia. So we decided to build on top of Julia for a number of reasons. First of all, it's open source, which of course makes understanding Julia internals a lot easier. It's also faster than some scientific computing language choices. It has good support for array-style programming, which is what we're trying to target. It's under active development with a strong community, and the Julia team has been extremely helpful to us in our efforts. In fact, we've been working closely with them. We meet with them every 2 weeks. They've visited us. We've visited them. And then finally, one reason that's kind of near and dear to my heart is that, unlike with some other scientific computing languages, writing a compiler for Julia in Julia doesn't seem out of the question. And that's because Julia makes it easy. Well, it's for a couple of reasons. But one of them is because Julia makes it easy to manipulate its own ASTs. And I'll talk more about that in a minute. All that said, Julia is not really the point, and the project is about high-performance productivity languages in general. But it made sense to use Julia for the prototype that we built. Still, I don't think there's a reason why these ideas couldn't transfer to other languages. OK, so let's talk about the compiler in a little more detail. So what I'm showing up here is our compiler pipeline. This is in contrast to the standard Julia compiler, which parses Julia source code into the AST and then transforms that to LLVMIR and finally generates native assembly code. So what we do is we intercept that process at the AST level. We introduce new AST nodes for the parallel patterns that I mentioned earlier. We do some optimizations on that, and finally we generate C++ code. So I mentioned a second ago that Julia has good support for manipulating its own ASTs. And in fact, there's a function called codeTyped that you can call to get the AST of any function. And this is very convenient for us, because we simply call that, and then we pass the result of that to the first phase of our compiler, which is called domain transformations. And the domain transformations phase produces this domain AST, or domain IR, intermediate language, which is like Julia's AST, except that certain AST nodes have been replaced with these new nodes that we introduce for parallel patterns. So a couple of kinds of map, reduce, and stencil. And taken together, we call those domain nodes. And after that, there's a parallel transformations phase, which replaces these domain nodes with what we call par4 nodes, each of which represents one or more nested parallel for loops. And loop fusion also happens at that stage. And finally, all that gets handed off to our code generation pass, cgen, which converts par4 nodes into OpenMP loops. So let's see what it looks like for the programmer. And this is an excerpt of the code for Blackscholes using Prospect. And as I mentioned before, we have a bunch of arrays. So this function Blackscholes takes 5 arguments. Each of them is an array, potentially a quite large one, depending on the problem size. And the Blackscholes algorithm which an excerpt of which I have here. There's a ... in the middle. I'm not showing all of it. The point is not really to read the code. The point is just to see that it does several computations involving adding, subtracting, multiplying, and dividing those arrays. So this code runs under Parallel Accelerator. And the thing to notice about it is that there's almost nothing different here compared to ordinary Julia. It imports our library at the top using Parallel Accelerator. And here's the ACC annotation on the Blackscholes function. That's it. Other than that, this looks how somebody would write Julia code anyway. This is a type annotation, which is optional in Julia. And it's also optional when using ACC. But generally speaking, ACC will do a better job of optimizing your code if you tell it what the types are. Next, I'd like to show you a demo. And the results that I'm showing won't be quite as drastic as you saw in the figure earlier, because I'm showing them on a machine with fewer cores and less memory. But I hope to still show you that prospect is fast. All right. And I'm doing this as a video. So what we have here is I'm running the Blackscholes benchmark that I showed you a minute ago. And this happens to be running under Julia Box, by the way, which is a nice hosted Julia service. So, and there it is. There's Blackscholes running under Parallel Accelerator. So there's, well, 3 numbers that I want to draw your attention to. The first is the number of iterations. I only did 10 million this time instead of 100 million. Next, this self-primed line. So this line is the amount of time that it takes for the Parallel Accelerator compiler to compile the code, plus the time it takes to run a trivial computation. So it's almost all compile time. And then finally, the self-timed line at the end is the actual runtime, so about 0.3 seconds. So that's under Parallel Accelerator. Let's see what happens under standard Julia. So I'm quitting Julia, and I'm starting it again with prospect mode turned off. And I'm running the same thing. So this time, note that self-primed is shorter, because this time we have, there's no compilation time. So whereas it was a second before, now it's a lot shorter. But now our actual runtime is 2.3 seconds. So that's Blackscholes. And I'll show you another demo in a little while. But back to the talk. All right. So with Blackscholes, that code was identical to the Julia version, except that we had to import the Parallel Accelerator library, and we had to use that ACC annotation. But I mentioned that one of the parallel patterns that we wanted to support was stencil. So in order to do this, stencil is a little less fundamental than the other things that I mentioned, like map and reduce. So in order to do this, we actually had to extend the Julia language. And we added a new language level construct to Julia, which we call run stencil, for expressing stencil computations. So I want to kind of give a very basic introduction to what a stencil computation even is, and with this example here. So a stencil computation generally involves an array of some kind, and you want to update each element in the array based on what the surrounding elements are. And a good example is this Gaussian blur computation, where you want to blur an image. So the array is represented as a 2-dimensional array of pixels, and in order to blur the image, you have to change the value of each pixel to a particular weighted average of that pixel's value and the values of the pixels around it. Okay, so what is this code doing? Well, we have this function called blur, and it takes a 2D array, which is our image, to blur, and it takes a number of iterations, which is the number of times we want to apply this blur procedure over and over. And then what we're doing is we're allocating a new 2D array that's the same size as the one we have, and then we have this run stencil thing. So what is going on here is we want to operate on our 2 arrays, the one that's the image and the other one that's the newly allocated empty one. And we have this expression here that starts with the do. And this is basically a lambda that binds 2 variables, b and a. And here, b is the newly allocated buffer, and a is the original image. And what this code does here is it says it indexes into B, and it says, okay, at index 0, 0, in B, we want to write into that image based on what's at all these different places in A. So that point in the original image plus the pixels that surround it. And what's interesting here is that 0, 0 is a relative index, meaning we actually do all this for each point in B. And then the indices in the expression on the right side of that assignment they're also relative indexes into the array. And then finally at the end we return, and we're returning A, B here. So this is swapped around from the B, A up here, which means that they'll go into the next iteration of the stencil and they'll be switched. So now we'll be blurring again the one that we've already blurred, and so on, for however many iterations that we specified. So I'll demo this one as well. By the way, all of the examples that I'm showing here are available in the package that we released. So there's an examples directory in our repository on GitHub, so you can go and find both Gaussian blur and Blackscholes as well as some others and run them yourself. So there it is. There's the parallel accelerator version, and there are two numbers there. The self-prime number, which again is the compilation time, that takes a little over a second, and then it takes about 20 seconds for the actual blur to run 100 iterations. And this is on an image that's 7,000 by 5,000 pixels or something like that. And then there's the regular Julia version. So again, I'm running in prospect mode none, and I'm running, and I'm actually going to speed up this video to run at 60x, because this is going to take a while. Any minute now. And there it is. So it took 668 seconds in plain Julia, as opposed to 20 seconds in Parallel Accelerator. So that's it for the demo. And I have one more. And here that is in plot form. So again, there's a comparison with MATLAB. And so MATLAB does a bit better than plain Julia on this. But as you can see, Prospect does better. And this number here for Prospect, this is like 4.5 seconds as opposed to the 19 you saw here. That's because this is running on a 20-core machine. And the Julia box demo that I was showing you, I think is 4 cores. Same image size, though. So that's Gaussian blur, or that's run stencil. And then I have one more set of results to show you, and this is also a use of run stencil. This time it's a 3D stencil. And this one I wanted to show you just so nobody got the impression that Julia is always slower than MATLAB. Here Julia outperforms MATLAB. But again, we have Prospect doing better than both in the single-threaded and parallel versions. All right, so before I wrap up, it would be negligent of me to not talk about DSLs a little bit. So when we're talking about ways to combine productivity and performance, we have to discuss DSLs. And I really like the three-way trade-off that the Delight team at Stanford formulated, which is between generality, productivity, and efficiency. So in other words, by using DSLs, we give up generality to get productivity and efficiency together. And the combination of all three is the magical unicorn that you can't have. So we were inspired by this approach. In fact, our domain AST and parallel AST that I mentioned were named after the domain IR and the parallel IR in Delight. The way that our approach differs, in my view, is mostly in how we present ourselves to the user. So we're really not trying to provide a DSL with its own semantics distinct from the host language. You still write your program in Julia. And of that, there is a particular sublanguage that our compiler is able to accelerate. So maybe you have to use run stencil, but that's as far as you will get from standard Julia. And the hope is that, barring bugs, you can expect the accelerated code to have Julia semantics, but just faster. The trade-off is that you can't put arbitrary code inside an accelerated function. Instead, ACC supports a subset of Julia that's focused on numerical computing on arrays. And there are a number of things that we don't support yet. For example, we don't support strings, which I plan to work on when I get home from Splash. So to wrap up, Prospect gives you a way to write scientific computing code in a productivity language, Julia, without sacrificing efficiency. And it does this by identifying parallel patterns in the code and by getting rid of many of the usual overheads of high-level array programming, like allocating intermediate arrays and checking array access bounds. And it's open source and available for you to try today. So thank you.
So we have time for questions.
So did you compare your results to compiling MATLAB?
That's a good question. So I don't think that we did. We did compare our results to versions written in C++. And the hope was to get something that was not necessarily going to be competitive with that, but that was within like a factor of 2 or 3 of that. We're not necessarily always there. So that's kind of like the dream. We end up getting, so I could show some more results. I didn't put anything that had the C++ comparison on these slides. But with one of our benchmarks, optical flow, which is also released in this package, we end up getting pretty close. It's like within 2 or 3x of this optimized C++ version.
Well, I guess more general question. I mean, people
Yeah.
have looked at like compiling MATLAB and so forth.
Right.
Before, and what do you say? Things you do better than MATLAB? Things you're not doing as well as compiled MATLAB?
Sure.
Talk about that comparison.
Yeah, okay. So I think I guess one difference is that because Julia is open source and because we have access to the internals of Julia, we can take advantage of knowing a lot about the internals of Julia. So we operate on the Julia AST, and all we do is add a couple of new AST node types. And in fact, Julia does type inference. So we take advantage of the type information that's already there in the AST. As far as I know, MATLAB doesn't have anything like that. So I don't know, if you were going to do, if you're going to compile, so I've seen some work, for example, at UPSLA last year on compiling MATLAB to X10. So if you're going to do this, you have to do that type inference yourself. And we were instead able to leverage the type inference that it already has.
I'm thinking about the MATLAB compiler provided by MathWorks.
Okay, well, again, it's not open source, so I can't really speak to the internals.
More questions? Yes.
So what does it look like if someone accidentally writes Julia that doesn't accelerate?
That's a great question. So what should happen is that our compiler attempts to accelerate it, fails, and then you get a nice message saying, could not accelerate this, we're falling back to regular Julia. In practice, that happens sometimes, and sometimes you get a code generation error. So we're working on that. And if you encounter something that's really egregious, you should file a bug.
Yes.
I'm just curious as to why you have a macro where the user chooses which functions to optimize instead of going throughout the entire program and optimizing everything.
Well, that's relevant to the question. So the question was, why pick out specific things to accelerate instead of just accelerating everything? And I think that's relevant to the question that was just asked, which is that we don't really optimize all of Julia. So we focus on this particular subset, which is numerical computing on arrays. And so, for example, we don't handle strings. So if your program prints anything, then we can't handle this. We actually encountered that in a really funny way. So when you use something that is deprecated in Julia, the way that the Julia compiler handles that is it inserts an AST node that's like the deprecation warning node. And the deprecation warning node compiles to something that prints the deprecation warning message. Because our compiler does not support strings, it failed to compile this. So so people fix their deprecation warnings really fast if they're trying to use parallel accelerator. But yeah, so that's the reason. It's because people, people want to write Julia. They want access to all of Julia, and our compiler doesn't support all of Julia. So the idea is that you have these numerical kernels that you pick out to accelerate, and you accelerate those. In theory, I think we could handle all of Julia, but it would add to the complexity of the library and. Yes, right. So as I guess I should be repeating the questions as they're being asked. So the previous question was, what do you do when somebody gives you something that you can't compile? And so that the best thing to do in that case would be to try and then print a warning saying, sorry, we couldn't optimize this. We're just falling back to regular Julia. In practice, that happens sometimes, and sometimes you get a code gen error. So that should happen all the time. Yeah, so we chose to compile to C++. Actually, this is an interesting question. So Julia compiles to LLVM. So why did we not target LLVM? And the reason originally was that we compiled to C++ because we wanted to be able to target some architectures that, that LLVM does not compile to, like the Xeon Phi, for example. In practice, we ended up not really doing that. And so all these results that I showed you were just on a regular Xeon processors. So we're actually now looking into targeting LLVM instead. So I don't know, what kind of backend did you have in mind? Okay. Yeah, okay. No, that's a great question. So our strategy so far for heterogeneous parallelism has been we have a runtime system that, and all these results were just on CPU alone. But kind of more experimentally, we also have a runtime system that tries to do some online profiling and scheduling things between devices. So we kind of have our own implementation of what OpenCL does. And when I say we, I mean people on my team, not me necessarily. Yeah, targeting OpenCL wouldn't, and there's no reason in principle why it couldn't be done.
And sorry.
Yeah.
Could I continue, because I'm also interested into distribution.
Yeah. We're just barely getting started on thinking about what a distributed runtime for this would look like. So keep your eye out.